Now, so far, we haven't really talked about the coordinate system of our vector space, the coordinates in which all of our vectors exist. But it turns out that in doing this thing of projecting, of taking the dot product, we're projecting our vector onto one which we might use as part of a new definition of the coordinate system. So in this video, we'll look at what we mean by a coordinate system, and then we'll do a few cases of changing from one coordinate system to another. So remember that a vector, like this guy r here, is just an object that takes us from the origin to some point in space, which could be some physical space, or it could be some space of data like bedrooms and thousands of euros for the house or something like that. What we haven't talked about so far really is the coordinate system that we use to describe space. So we could use a coordinate system defined by these two vectors here. I'm going to give them names. We called them I and j before. I'm going to give them names E1 and E2. I'm going to define them to be of unit length, so I'm going to give them a little hat, meaning they're of unit length. And I'm going to define them to be the vectors 1, 0 and 0, 1. And if I had more dimensions in my space, I could have E3 hat, E4 hat, E5 hat, E a million hat, whatever. Here the instruction then is that R is going to be equal to doing a vector sum of 2 E1s or 3 E1s and then some number of E2. So we'll call it doing 3 E1s hats plus 4 E2 hats. And so we'll write it down as a little list, 3, 4. So R is the 3, 4 here is the instruction to do 3 E1 hats plus 4 E2 hats. But if you think about it, my choice of E1 hat and E2 hat here is kind of arbitrary. It depends entirely on the way I set up the coordinate system. There's no reason I couldn't have set up some coordinate system at some angle to that. Or even use vectors to find the axes that weren't even at 90 degrees to each other and were of different lengths. I could still have described R as being some sum of some vectors I used to define the space. So I could have, say, another set of vectors B, and I'll call B1 here in the vector 2, 1, and I could have another vector here, B2, as the vector minus 2, 4. And I've defined it in terms of the coordinates E, and I could then describe R in terms of you're using those vectors B1 and B2. It's just the numbers in R would be different. So we call the vectors we use to define the space, these guys E or these guys B, we call them basis vectors. So the numbers I've used to define R only have any meaning when I know about the basis vectors. So R referred to these basis vectors E is 3, 4. But R referred to the basis vectors B also exists. We just don't know what the numbers are yet. So this should be kind of amazing. R, the vector R, has some existence in a deep sort of mathematical sense, completely independently of the coordinate system we use to describe the numbers in the list describing R. R, the vector that takes us from the origin to there, still exists independently of the numbers used in her. Which is kind of neat, right? Sort of fundamentally sort of idea. Now, if the new basis vectors, these guys B, are at 90 degrees to each other, then it turns out the projection product has a nice application. We can use the projection or dot product to find out the numbers for R in the new basis B, so long as we know what the B's are in terms of E. So here I've described B1 as being 2, 1, as being E1 plus E2, twice E1 plus 1 E2. And I've described B2 as being minus 2 E1s plus 4 E2s. And if I know B in terms of E, I'm going to be able to use the projection product to find R described in terms of the B's. But this is a big if. The B1 and B2 have to be at 90 degrees to each other. If they're not, we end up being in big trouble and need matrices to do what's called a transformation of axes from the E to the B set of basis vectors. We'll look at matrices later, but this will help us out a lot for now. Using dot products in this special case where the new basis vectors are orthogonal to each other is computationally a lot faster and easier. It's just less generic. But if you can arrange the new axes to be orthogonal, you should, because it makes the computations much faster and easier to do. So you can see that if I project R down onto B1, so I look down from here and project down, at 90 degrees, I get a length here for the scalar product, and that scalar projection is the shadow of R onto B1, and a number of the scalar projection describes how much of this vector I need. And the vector projection is going to actually give me a vector in the direction of B1 of length equal to that projection. Now, if I take the vector projection of R onto B2, going this way, I'm going to get a vector in the direction of B2 of length equal to that projection. And if I do a vector sum of that vector projection plus this guy's vector projection, I'll just get R. So if I can do those two vector projections and add up their vector sum, I'll then have RB being the numbers in those two vector projections. And so I've found how to get from R in the E set of basis vectors to the B set of basis vectors. Now, how do I check that these two new basis vectors are at 90 degrees to each other? I just take the dot product. So we said before the dot product cos theta was equal to the dot of two vectors together, so B1 and B2, divided by their lengths. So if B1 dot B2 is 0, then cos theta is 0, and cos theta is 0 if they're at 90 degrees to each other, if they're orthogonal. So I don't even need to calculate lengths, I'll just calculate the dot product. So B1 dot B2, here, I take 2 times minus 2, and I add it to 1 times 4, which is minus 4 plus 4, which is 0. So these two vectors are at 90 degrees to each other. So it's going to be safe to do the projection. So having talked through it, let's now do it numerically. So if I want to know what are described in the basis E, and R's pink, right? So if I take R in the basis E, and I'm going to dot him with B1, and the vector projection divides by the length of B1 squared. So R in E dotted with B1 is going to be 3 times 2 plus 4 times 1, 4 times 1, divided by the length of B1 squared. So that's the sum of the squares of the components of B. So that's 2 squared plus 1 squared. So that gives me 6 plus 4 is 10 divided by 5, which is 2. So this projection here is of length 2 times B1. So that projection there, that vector, is going to be 2 times B1. So that is, in terms of the original set of vectors B, original vectors E, RE dot B1 over B1 squared times B1 is the vector, is 2 times the vector 2, 1, is the vector 4, 2. And I can do then now this projection onto E2, so I can do RE dotted with B2 and divide by the length of B2 squared. And RE dot B2 is 3 times minus 2 plus 4 times 4 divided by the length of B2 squared, which is minus 2 squared plus 4 squared. So that's 3 times minus 2 is 6, minus 6 plus 4 times 4 is 16. So that's minus 6 plus 16 is 10. Divided by this length here is 4 squared is 16, 2 squared is 4, so 20. So that's equal to a half. So this vector projection here is that guy times B2, so that's RE dot B2 over the modulus of B2 squared, that's my half, times the vector B2, so that's a half times the vector B2, which is minus 2, 4. Now if I add those two together, 4, 2, this bit, that vector projection, plus this vector projection, so this guy is going to be a half B2 plus half minus 2, 4 is minus 1, 2. If I add those together, I've got 3, 4, which is just my original vector R, 3, 4. in the basis E. So in the basis of B1 and B2, our B is going to be 2.5. Very nice, 2.5. So actually in the basis B, it's going to be 2.5 there. So our B is 2 times B1 plus 1/2 times B2. Very nice. So I've converted from the E set of basis vectors to the B set of basis vectors, which is very neat, just using a couple of dot products. So this is really handy. This is really cool. We've seen that our vector describing our data isn't tied to the axes that we originally used to describe it at all. We can redescribe it using some other axes, some other basis vectors. So the basis vectors we use to describe the space of data and choosing them carefully to help us solve our problem will be a very important thing in linear algebra and in general. And what we've seen is we can move the numbers in the vector we use to describe a data item from one basis to another. We can do that change just by taking the dot or projection product in the case where the new basis vectors are orthogonal to each other.